couple of minutes that we have here, let's think about a couple of reactions that will be important, and perhaps one new mechanism. So actually, I'm going to go back up for a second here to this ladder, which we'll refer to a few times in the next couple of days. As mentioned, most of the reactions that we're going to see will allow us to go down reactivity using the fundamental mechanisms that we've already seen. However, one or series of really useful reactions are to make these acyl chlorides here. Because once we make the acyl chloride, and this doesn't just have to be a methyl group here, it could be all sorts of other stuff dangling off on this side, we can use that acyl chloride to make all these other carboxylic acid derivatives. So that's what we'd like to do. These acyl chlorides actually are quite difficult sometimes to work with. They just get hydrolyzed by water, so any moisture in the air or water on your glassware or something like that, will turn your acyl chloride that you worked so hard to make just into a carboxylic acid. So these we have to work with quite carefully, keeping air and moisture out all the time. So there's a variety of ways to make these compounds, and we're going to look at just one in particular. But I just want us to be aware of three common methods, and all of these come from carboxylic acids. So carboxylic acids are quite convenient to get. You can buy them quite readily. They're stable, so they'll sit on the shelf or in the flammables cabinet for some time. So you can have the carboxylic acid, and then when you're ready to use this in a series of reactions, you might want to first turn it into the acyl chloride. One way is using this reagent here, SOCl2, which is thionyl chloride. And you may have seen this reagent in OChem 1 of turning an alcohol into a chloro substituent. So it's also used for that. And that's the one that we're going to consider in a little bit more detail in a minute. But what this does is it generates the acyl chloride, sulfur dioxide, and HCl. We're not going to go through the mechanisms for these other two, and I don't expect us to memorize them. But just to be aware that there are other ways to do this. You can take some carboxylic acid here, like acetic acid, take this compound, which is phosphorus, this trichloride, and make the acyl chloride. The stoichiometry here happens to be that each of these chloro substituents on the phosphorus can be used to substitute a hydroxyl. So this is nice because you can take 1 mole of this compound, which is pretty reactive, and react it with 3 moles of your carboxylic acid. This next one doesn't really work out 1 to 5, but this is phosphorus pentachloride. Chloride, that's an E at the end, which can be used also to turn a carboxylic acid into the acyl chloride that was shown here. So something like acetic acid, which will be our new acetone. It's our generic carboxylic acid. PCl5, and use this to make the acyl chloride. So let's consider briefly this thionyl chloride mechanism. And how do we actually turn our carboxylic acid into an acyl chloride? And when thinking about it, probably what we end up wanting to do is we need to make this here, OH, from a bad leaving group to a good leaving group. So it comes back to those same ideas, and that's one of the reasons for going through it. Some of those same principles that we've seen about reactions today, turning bad leaving groups to good leaving groups, occurs here. It's just a little bit more complicated. And there's different ways to draw this mechanism. I think I have the drawing here is in the Sorrell book to be consistent. But if you see slightly different arrow pushing in your different organic book that's your favorite textbook, they're just variations of the same thing. So let's take this reagent here, SOCl2. This is thionyl chloride. So it's a difficult reagent to buy. It's regulated, and it's quite reactive. It's kind of like a yellowish liquid. It smells pretty bad and is highly reactive. But we can just write it out like that. And one way it's thought the mechanism, so make it a little larger if I can, is just like our carbonyl group always showed a dipole here. Same thing with a sulfur-oxygen bond. This goes back to the solvent DMSO, we could actually write a resonance structure, remove these electrons up onto this oxygen, so it's O minus, S plus, which means that sulfur is electrophilic. So we'll actually have a lone pair of electrons on this oxygen attack. This is what looks different here. This is all the same. And we'll use this to help exemplify something. So what we've done is use a lone pair of electrons on that oxygen to form a bond with the sulfur. And I guess I'll draw it even in more steps than we see, I think, in our book. And we have a chloride here and a chloride here. And we have a positive charge on this oxygen. Now, right away, one of the things that we can imagine is that we have these two really good leaving groups here. So let's kick out one of those leaving groups. So this is all the same. Still that formal charge on the oxygen, and we've generated Cl minus. So now what we've done is we have a good nucleophile here with chloride that we've generated, and we have this very electrophilic carbon in the carbonyl group because we have a positive formal charge in that oxygen. And we can imagine then having our nucleophile attack. Let's move these electrons up onto this oxygen. I want to draw this big enough here so that now we have this. It's all the same. We have our OH here. I want to expand the OH. And we have the chloro down here. Let's make sure that's actually attached properly. We have this. And now this is drawn in a couple of different ways, but what we need to do is I'm going to make this a little bit smaller. Is our products of the reaction are the acyl chloride that we're really interested in, SO2, sulfur dioxide, and hydrochloric acid, H2O. So looking at our structure down here on the bottom, it's looking like this, maybe this part around here will end up being, well, maybe this part here, I should say, will end up being our acyl chloride. Maybe this is going to be SO2, sulfur dioxide. And then that other chloro looks like it's going to generate the HCl. So that's probably where the hydrogen comes from. So one way of drawing this mechanism, so we'll make this a little bit bigger again, is let's consider breaking this carbon-oxygen bond so that we can form a sulfur dioxide, which should be quite stable. Let's then use this to pick up the proton, and then form our carbon-oxygen double bond, which is what we're interested in. Let's see how that works for our product. So we're going to have R group, carbon double bonded to oxygen, bonded to chloro. So there's our acyl chloride. Then here we're going to have, we broke this carbon-oxygen bond, so we're going to have S double bond O, double bond O. We broke the sulfur chlorine bond. Plus, last, we're going to have, actually, let me put it to the side. It's easier to compare. And last, we'll have HCl. So we'll have hydrogen chloride here, so HCl. So those are our products. This is the acyl chloride that we want. Sometimes these are known as acid chlorides. Sulfur dioxide. And of course this is hydrochloric acid. And here, I know the mechanism looks different than things that we've seen before. I don't want us to really memorize this mechanism, but just to be aware of it. Notice that what we're doing in the end is we're going to have this carbonyl oxygen attack the sulfur. There's a dipole here. Kick out our good leaving group, which is going to be our chloride that we're going to have here. Then our good leaving group ends up being the sulfur dioxide, which then we can generate HCl as well. This reaction is going up that order of reactivity in terms of the carboxylic acid derivatives. So the reason this really works here is that we're forming, so why does this work? Going up that ladder of reactivity. One is that we're forming stable products, not necessarily the acyl chloride, but SO2 and HCl in particular. So the driving force is forming the sulfur dioxide, which will leave the reaction and pull the reaction forward. And then two, this is entropically favored. In other words, delta S is positive. So entropy is favored because we're starting with 2 molecules and we end up with 3 molecules down here. So 2 molecules into 3. So this helps highlight something. If we're going in an energetically unfavorable way in that ladder of reactivity, somehow we have to pay energy into the system for this to occur. And we can do this by taking this thionyl chloride is quite reactive. We're turning it into things that are actually now quite stable. And we still have one thing that's reactive, but 2 that are going to be quite stable. And we're also taking 2 species. So if you have 1 mole of each of these, you'd end up with 1 mole of each of these. So you'd have 3 moles in the end. So it's entropically favored. So I wanted to use that reaction to highlight a couple of those other fundamental features. So that's where we're going to be at for today. We've finished our discussion with the Wittig reagents to see some of the similarities with our other carbonyl chemistry. And then I'll scroll back up because this helps summarize a lot of the next sort of chemistry that we're going to see as we introduce now these compounds that have, pointing here to the top, now leaving groups. The leaving groups are going to be different. Some will be better than others. We're going to be able to predict the relative reactivities of the leaving groups. We now have some sort of a mechanistic or structural explanation as to why. We went up the ladder from the carboxylic acid to make the acyl chloride. Now what we're going to do is turn this acyl chloride into a bunch of other things next time. So we'll have a quiz starting at 9 o'clock next time. That's going to cover, I can imagine, 1 question about Wittig chemistry, 1 question about carboxylic acid derivatives, and then we'll continue forward with all of this carboxylic acid chemistry. So if you have any questions about any of this stuff or the exam or other things as we go forward,